Okay, today is Saturday, May 9th, 2020, and this is Unit 4, Reactions. We're 6 days away from the AP exam. So we're going to go over the different types of reactions we've talked about in class. I'm going to not talk about acid-base today. I'll do that on another day. But there's various types of reactions we need to deal with, and also covers the concept of stoichiometry. So stoichiometry is simply using a chemical equation. A chemical equation is the centerpiece of chemistry, and it only speaks in one language. It speaks in the language of moles, or in numbers of atoms and molecules. So for this equation, for example, you need 2 atoms of silver and 1 molecule of hydrogen sulfide in order to produce this reaction here. And it doesn't mean you need exactly 2 moles in 1 mole. It means you need twice as many moles of silver as you have of H2S. So if I have 100 moles of this, I need 50 moles here. If I have 1,000 moles here, I need 500 moles there. So what chemical equations do is they match up molecules, numbers of atoms and molecules. They don't care about mass or grams. They don't understand that. If I'm trying to, in class, form groups, and let's say I want 2 girls and 1 boy in each group, let's just, for a simple example. I don't care that the girls weigh 100 pounds or 200 pounds, or that the boy weighs 300 pounds or 50 pounds. Who cares? I'm trying to match up 2 girls and 1 boy. So similarly, chemical equations don't care how much these atoms or molecules weigh. Grams mean nothing to the chemical equation. What grams are is something that we can measure in our world on a scale, on a triple beam balance or some sort of an electronic scale to get grams. And then we can use these translators called molar mass conversions, which tell you for any particular substance how many grams 1 mole is. So for silver, 1 mole is 107.9 grams. And so once we know that, we can convert into the language of moles, which is the language that the chemical equation speaks in. And then when we need to get out back to our world, we can convert from moles back into grams. Remember, a chemical equation is like a formula. If I tell you I'm going to give you 100 pounds of flour and 500 eggs and 300 cups of sugar, and I want you to make me 100 cakes, well, you can't do it because you don't know what the recipe is. How many cups of sugar do you need? How many eggs do you need? How much flour for each cake? And then you can figure out how many you'll need for 100 cakes. And that's what this is doing. This is the recipe in chemistry. So we put in the ingredients and you put it through the recipe, and then it tells us what we're going to come out with. Okay, so this is not meant to be a full lesson on all of these chemical reactions. It's really just to give you 1 or 2 examples and then to move on. Hopefully this comes back to you with this. All right, so let's read this question. How many grams of H2S is required to produce 8.3 grams of Ag2S? So here's H2S, here's Ag2S. So what we're going to do is, it's asking us how many grams of H2S. So we come down in our world, we want to know how many grams of this we're going to need if we're going to get 8.3 grams of this. So we're going to say we want 8.3 grams. We're in the grams row, and in this column of Ag2S, and we want to produce that. So how many grams of this are we going to need? So we put a question mark there. So this is a chemical reaction that's flowing from left to right. We're putting in this to get this, but mathematically, in this specific case, we're working backwards. We're starting off with what we know, and we're working backwards to get what we don't know. So there's no way to get directly from here to here. You can't go from grams of Ag2S to grams of H2S directly. What you have to do is use the recipe. So you have to move from grams of Ag2S, use your molar mass to convert that into moles of Ag2S, and then find out the relationship between moles of Ag2S and moles of H2S. That'll get you over to this box. And then get from moles of Ag2S using this translator right here to get you back out into the world of grams, which is our world right there. So it's a 3-step process. Now you don't have to write down this number and then this number. You really just put them together in one equation, and then you finally come to this number. So remember how we did this. You build a bridge, and what we want to know is how many grams of H2S. So way over here on the right, I'm going to write grams of H2S. Always remember to write both unit of measure and the substance. Okay, don't get lazy and stop doing that. You got to do that every time. Okay, what we're starting with is 8.3. We're going to put that way over here because we're going to need a few conversions here. 8.3 grams of Ag2S, unit of measure and the substance. Now it's going to take 3 conversions, one from here to here, one from here to here, and one from here back down to here. Now you don't want to have to draw this graphic organizer on an AP exam. I mean, hopefully you kind of visualize how you put these equations together. So there's one of our conversions. There's a second conversion. And there's the third conversion right there. So remember how we did this. We want to go from here to here. So there's an equation here. We equate 1 mole of Ag2S with 247.87 grams of Ag2S. So what that means is I can say there's 1 mole Ag2S over 247.87 grams of Ag2S, or there's 247.87 grams of AgS over 1 mole of Ag2S. So which one do I want? Well, I want grams of Ag2S to disappear because it's not in my final answer, grams of Ag2S, so I know it needs to go away. So let's set it up so it cancels out. So I have 1 mole and that's going to be 247.87. And on the AP exam, generally they're going to round the numbers. They're not going to be dealing with decimals for things like this. Okay, so grams of Ag2S cancels with grams of Ag2S. Okay, now we're ready to go from moles of Ag2S. Now we're sitting in this box over to moles of H2S. So we need moles of Ag2S to disappear and moles of H2S to appear. So we have a relationship. There's 1 mole of Ag2S for every 1 mole of H2S. So you can put this one over this one, or you can put this one over this one. Which one do you want to do? Well, we want moles of Ag2S to disappear, so we're going to put moles of H2S over moles of Ag2S. And moles of Ag2S cancels. And there we go. Now we're sitting in this box. We're ready to come back out into our world and get our final answer. How many grams of that are we going to need? So here's our translator. So 1 mole of H2S for every 34.09 grams of H2S, or 34.09 grams of H2S for every 1 mole. Which one are we going to want to use? Well, we need grams of H2S to appear in the final answer, and we need moles of H2S to disappear, so it's going to be this one. Put moles of H2S on the bottom. And moles of H2S cancels. And now you're ready to do your calculation. Okay, and what we get is 1.14 grams of H2S. So what that's telling us is if we want to end up with 8.3 grams of Ag2S, we need to start off with 1.414 grams of H2S plus at least enough silver. We don't want to run out of silver, so we have to have enough silver to make that work. Okay, so that's how you do a grams to moles type of stoichiometry. This can be used for solids, it can be used for gases, pure gases, or it can be used for pure liquids like water. It can't be used for mixtures like solutions like salt water. Then we have to use molarity. We'll get into that later. So anything that's a pure substance, either a pure or some sort of pure compound like this, okay? It's grams to moles because you have to be able to calculate the molar mass to use grams to moles. Okay, next up we're going to do gas stoichiometry. So let me pull this down a little. There's only one formula in gases you really need to know. There's a couple others that are useful, but this one's critical. Is PV equals nRT. Pressure times volume equals number of moles. And number of moles is a variable here, so they use the letter N. They don't use MOL. That's a unit of measure. It comes after the number. So it's number of moles times the gas constant. There it is. There's a couple of versions of the gas constant, but this is the one you use with PV equals nRT. And the temperature. And so what's important about this gas constant are the units of measure. And I wrote them kind of small, but it's liter atmospheres over moles Kelvin. So it tells you your temperature has to be in Kelvin. If they give it to you in centigrade, you have to add 273 to that to get it into Kelvin. If they give you your pressure in pascals or in torr, you have to convert it to atmospheres. Okay, so let me do that, write that up here real quickly. So 1 atmosphere, these are all about the pressure in a standard room, at sea level, about where we live. 1 atmosphere. Okay, that's 760 torr, which equals 760 millimeters of mercury, which equals 101,300 Pascal, which equals 101.3 kilopascal. So if you need to convert from, say, torr to atmospheres, you just use these as a conversion factor. 1 atmosphere over 760 torr, or 760 torr over 1 atmosphere. Between kilopascals and atmospheres, you use this over this, or this over this. You can create conversion factors out of those. Okay, what is pressure? Let's talk about this little mini lesson on gas law. Probably the only one I'll give you. Pressure, think of pressure as how many times molecules hit the side of the container. It's my loose definition. It's how often. In molecules or atoms, a gas molecule could either be a molecule, or a gas particle could be either a molecule or an atom. So we call it particles. So how often particles. And in gases, we don't really care about protons, neutrons, and electrons. These are not reacting chemically. They're just acting like little balls flying around in space, because that's what a gas is. It's unattached atoms or molecules. They're not reacting chemically with anything else. So we just call them particles. Hit the side of the container. Temperature is how fast the molecules are moving. Okay, you can think of that as their speed. If you're only dealing with one type of gas, then what temperature really tells you, to be proper, is kinetic energy. It's the average kinetic energy of the molecules. And if you remember from physics, that equals 1/2 mv squared. So let's say I have two molecules, a larger one and a smaller one. If there's a certain temperature, that means both the larger and the smaller molecules have the same value for kinetic energy. Well, look at this. An atom or a molecule, a particle, has a mass and a velocity. So if it's a bigger mass, it has to have a smaller velocity. If it's a smaller mass, it has to have a higher velocity, meaning it's moving faster. So that those two multiplied together in this equation would both give you the same kinetic energy, assuming you had two different gases. If you're only dealing with one gas and it all has the same mass, then the change in temperature is going to change kinetic energy, and the mass of the particle is not going to change if it's the same particle. So the only thing that could change is the velocity, the speed. So that's why you can think of temperature as how fast particles are moving. And of course, the last one, volume, is obvious. It's how big the container is. Okay, so that's your mini lesson on gas laws. They're really easy because it's not chemistry. It's really more physics and objects flying around and hitting each other and bouncing off walls and doing those type of things. So it's not chemical reactions that are going on here. Okay, so let's look at this flow chart that I made for this. It includes, it's a simple equation for water, and it includes grams down here and molar mass to get you into moles, just like the last problem. But it also includes up here that if you're given a certain pressure, volume, and temperature, using PV equals nRT, you can figure out how many moles. And remember, moles is the only language that the chemical equation speaks. Okay? So you can either come in through this side and go across the equation and come out the other side, come out with a number of grams, or you can come in with a number of grams. And as long as it's a gas, you can come out on the top and figure out how many moles you have or what pressure or what have you. Okay, so let's just do one problem on this. Okay, so let's take that equation above and let's work with this. And I had to make a couple changes for my old problem. How many grams of H2 are required to create 6.4 liters of H2O at 293 Kelvin and 1.5 atmospheres? Okay, so you're trying to create liters up here of H2O. So you're trying to get up here with liters. And you're starting off with grams of H2. So, and actually, I put the question mark in the wrong place. It's how many grams of H2. So the question mark is down here. And up here, you're trying to end up with 6.4 liters of H2O. So I'm going to put the 6.4 here. Okay, so the chemical reaction is proceeding from left to right. It moves in this direction, but our math is going to, it doesn't always do this, but it does in this case. It's going to go from right to left. We start off here and we end up down here. So let's think about what do we have to do. We need to be able to come up with some number of moles of H2O. How many moles of H2O? Because this equation only speaks in moles. So what we're going to do is use the formula N equals PV, this formula right here. So pressure is 1.5. I'm going to do something I shouldn't do and not write the units of measure just to save space. It's 1.5 atmospheres times the volume, which is 6.4 liters. That's the volume we want. Over RT. R is 0.0821 liter atmospheres moles Kelvin, and since I'm dealing with all those units, I'm good to go. That's why I can kind of skip the units of measure here. And temperature is 293. You got to be sure it's in Kelvin. Okay, and when we calculate that, what we get is 0.04 moles. So I'm going to go ahead and jump down here. I'm going to write it right there. That's how many moles of water that we're talking about. 0.4 moles of water. Okay, so now I've converted from all of these data up here into moles of water that I have based on the pressure, temperature, and volume. And now I'm going to convert from moles of water to moles of hydrogen gas, and we see that it's a 1-to-1 relationship, 2 moles to 2 moles. So it's a pretty easy relationship. Finally, I want to know how many grams of hydrogen, so I'm going to come out the other side down here, and I'm going to use the molar mass to figure out how many grams of hydrogen it would take to produce this many liters of water, and it would be water vapor at particular temperature and pressure. So let's go ahead and write this. So what we want over here on this side of the equation Okay, and since we did these calculations already and just came directly down into moles, I'm not going to show all of these calculations in the equation. So now I'm simply going from moles of water to moles of hydrogen gas. And you can see it's 2 to 2. Okay, and so moles of H2O cancels moles of H2O. And now I use the molar mass conversion to get from moles of H2 out to grams. So I need grams of H2 on the top. And remember, when you're writing a molar mass conversion, it's always 1 mole. Don't get confused by that. That's the one you used for this part of the equation. But when you're coming out, it's always 1 mole equals some number of grams. Okay? All right, so moles of H2 cancels the moles of H2. The last man standing is grams of H2. And so you go ahead and run that number. And we get 0.8. Close enough. 0.81. Okay, I'm not worrying about significant figures here. Okay, so that's how you would mix up working with grams to moles and with gas laws, PV equals nRT. You can use PV equals nRT to figure out number of moles. Once you know number of moles, you can work with a chemical equation here. And then that's it. Okay? Okay, now we're getting into solution stoichiometry. So what that is a mixture. It's not a pure liquid. It looks like a liquid, but it's not a pure liquid. Just think of salt mixed into water. So the salt would be called a solute. It's what's being dissolved. The water would be the solvent. It's what's doing the dissolving. And when you put the two of them together, it's called the solution. Okay, so solute is the smaller of the two. It's the shorter word. It's 6 letters long. Solvent is 7 letters. There's more of that. That's the water. and the longest word of the two, solution, is 8 letters. That's the two of them together. So that's kind of the way to remember it. By far and away, the most important one you're going to use is this one, molarity, and it's moles of solute. Just think of that as salt for liters of solution. Solution is the salt water together, salt and the water together. So it's moles per liter. One problem with molarity is it's affected by temperature, because if you freeze that salt water, it expands. The water expands, and so you have a different number of liters of ice than you would have liters of liquid water. Nevertheless, it is the one that's used almost all the time, and if they ask you a question, a solutions question, it's going to be in molarity, almost certainly. But let's talk about the others. Molality is moles of solute, so it's just like the molarity, but the difference, the bottom is totally different. It's kilograms, it's mass of solvent, okay? Kilograms of solvent, not of the whole solution. So first of all, it's mass versus volume of liters, and it's solvent, which would just be the water in salt water, versus the entire solution of salt water. That's called molality, okay? Next is mass percent, and it's simply the grams of the solute over the grams of the solution. That would be the mass percent. So it's the percentage, and then you multiply by 100% to give you a percentage. So that's the mass percent. Mole fraction is kind of like mass percent, except it deals with moles, not with grams, and it's a fraction. It's not expressed as a percentage. So it's expressed as a decimal usually. So it's the moles of one solute over the moles of all the solutes and solvent. Okay, so you're in moles, you have to be in moles, and it's one solute over the moles of everything else put together, including the one that you're taking the mole fraction of. That's used in an area of chemistry we didn't deal with in class. It's not part of the AP exam, but you may be asked a mole fraction question. Finally, parts per million. Parts per million is just like percent composition by mass, except percent composition has a denominator of 100. That's what percent means, per 100, whereas this is per million. So it's same as grams of solute over grams of solution, just like up here, but you multiply, instead of by 100%, you multiply by 1,000,000. And that's used for something that have very low concentrations, like say arsenic in drinking water. There's not very much of it, but they're allowed to have a certain number of parts per million or even parts per billion. So it just changes the denominator. And finally, dilution of a solution. Just think of lemonade. You make some lemonade, you mix in the lemonade mix with the water, and it's too strong, it's too sweet. So what you want to do is add water to dilute it down so that it's not as sweet and so it tastes just right. And this is just a little formula. I'll show you one example of that. It's the molarity of at the beginning. I could put, instead of 1, I could have put beginning volume at the beginning equals the molarity after you've added the water times the volume after you've added the water. So it's just a simple equation for that. Okay, so let's work some problems with this. And I may not work as many as you see on the page. I may just decide, that's enough. Okay. So, molarity, 500 milliliters of solution with 6 moles of KOH. So remember, you always want to convert things to liters. And you should learn to do this just quickly off the top of your head, not have to write out a math equation for it. But anytime you want to go milliliters to liters, you just slide the decimal over 3 places. So 500 milliliters equals 0.5, and you can put the other zeros, liters, okay? If I wanted to do it mathematically, it would look like this. 500 milliliters times, there's 1 liter for every 1,000 milliliters. So milliliters cancels, and you have 500 times 1 divided by 1,000 equals 0.5 liters, okay? So, but you should learn this decimal adjustment real quick so you're not wasting time. You should always in solutions convert to liters, okay? So we'll do that as part of this problem. Okay. So it wants to know molarity. So what I know molarity is, break that down into its components. It's moles of solute, which in this case is KOH, potassium hydroxide, over liters, and I could write KOH plus water, but it's just easier to call it solution and abbreviate that SOLN. But it's really the KOH, the solute, plus the water, which is the solvent. And that's that. Okay, so what I need to have is liters of solution on the bottom And I need to have moles of KOH on the top. So it's telling me there's 500 milliliters of solution. Okay, so what I'm going to do is I'm going to write a fraction here, and it gives me 6 moles of KOH, and that's what I want on the top. So I'm going to go ahead and write 6 moles of KOH. On the bottom, I want liters of solution. Well, it gave me milliliters, so I'm going to write 500 milliliters of solution. It told me that's what I have. And the only thing I need to change is get milliliters to convert to liters, which is what I did up there, except I got to do it upside down because the milliliters is on the bottom. So it's 1,000 milliliters of solution. Always write both the unit of measure and what you're talking about over 1 liter of solution. So milliliters of solution cancels and you end up with moles of KOH over liters of solution, which is what I want in my final answer. So now you can simply do the math, and that's going to equal 12, which 12 moles of KOH per liter solution, which you should write actually the final answer as 12 molar. 12 molar is the final answer. That's what that is, molarity. Okay. What is the molarity of 60 grams of NaCl dissolved in 400 milliliters of solution? So again, I'm trying to find, write down what you're trying to find. You always want to know where you're going before you start. Okay, so I'm going to end up with moles of NaCl, and I need to end up with liters of solution. Okay. All right, so what am I starting with? Well, I'm starting with 60 grams of NaCl. I want NaCl on the top, so I'm going to put that on the top up here. And on the bottom, I have 400 milliliters of solution. And again, if in your head you want to quickly convert that to 0.4 liters, that's fine. Okay. So I'm starting off with solution on the bottom, NaCl on the top, NaCl. So take them one at a time. Let's convert from grams of NaCl to moles of NaCl. So you do that using the molar mass. And if we get our, over here, Na is 22.9 and Cl is 35.45. So that's going to give you 58.44 is the molar mass of NaCl. So I'm going to write 1 mole, because I'm trying to get to moles of NaCl, for every 58.44 grams. Okay, so grams cancels with grams, and now I have moles of NaCl on the top, which is what I want. Now I got to get milliliters of solution into liters, so again it's 1,000 milliliters. Milliliter solution cancels with that. So now I have moles of NaCl over liters of solution. That's what I want. So now you can do the calculation. And that gives me 2.6, we'll just round it there, 2.6 moles of NaCl per liter, or 2.6 molar. Okay, so that's how you do those calculations. All right, so study those, practice them, cover them up, see if you can do them by yourself. Okay, all right, I'm going to skip the third one. Let's keep moving on. Preparation of a solution. So how many moles? This is a very probably a question they could ask you. How do you prepare a solution of so much molarity, of such a concentration? So how many moles of LiF are required to prepare 600 milliliters of a 2.5 molar solution? Okay, so now we're starting at the other end. We're starting at 2.5 molar. So write out what that means. It means 2.5 moles of lithium fluoride over 1 liter of solution. Okay, and what you want to end up with is some number of moles of LiF. So I'm going to come way over here because this is what we're trying to find, moles of LiF. So you'll notice something, that the liters of solution totally disappears. We just want moles of LiF. That's what we're trying to find, and we're already given 2.5 moles of LiF per liter of solution. So we need to make this disappear. So they give us 600 milliliters here. So first thing is, let's convert liters into milliliters. So that means we're going to take 1 liter of anything for every, let's say, solution, since that's what we're dealing with. Always want to write what you're talking about. For every 1,000 milliliters of solution. So this cancels with this. And now you have milliliters of solution, and up there you have 600 milliliters of solution. So you're going to multiply times 600 milliliters of solution. Okay? And it doesn't have to be over anything. It just is. It's 600 milliliters, so that cancels with that. So what you've done is you've gotten rid of all the liters and milliliters, and the only thing you have left is this way over here, which is moles of LiF. So now when you do that, you're going to get... Should be able to do this in my head, but I'll do it on... Okay, that's going to give you 1.5 moles of LiF. Okay, so it's 2.5 times 1 times 600 divided by 1,000 divided by 1. Okay, there you go on that. All right, how many grams of MgO, magnesium oxide, are required to prepare 432 milliliters of 3 molar solution? Okay, so they're given these two numbers and you're asked for how many grams. So let's come down here. Grams of MgO, and you're trying to figure out how many. Okay, so what are we starting off with? 2.5 molar solution, or 3 molar solution, excuse me. So it's going to be, let's start way over here on the side, 3 moles of MgO, that's your solute, for every 1 liter of solution. So let's set back and see what has to happen. We need to get moles of MgO into grams of MgO. Well, we can do that using a molar mass conversion. Then we need to make liters of solution just disappear, and we have this up here to make that happen, just like we did in the last problem. So let's go ahead and take care of the top first. So MgO, okay, so magnesium oxide has a molar mass of 40.31 grams per mole. So we need to convert that to moles. So we are going to say, excuse me, we need to convert it into grams. We're going from moles to grams. So 40. So we have moles of MgO canceling there. So now we have grams of MgO on the top, and that's what we want. In fact, that's all we want. So we have to make this disappear. So how do we do that? Same way we did last time. We say 1 liter, and I'm going to try to abbreviate it for every 1,000 milliliters. That's true of anything. And then you're going to multiply by 600 milliliters of the solution. So I should be putting solution, solution, solution. Just trying to save space. Okay, so liters of solution and liters of solution, milliliters of solution, milliliters of solution. So you have this times this times this divided by 1,000, and that will give you your answer. And that gives you 72.6 grams. Okay? All right, so just learn to line up the units. The next one is the same. I'm going to skip that one. Okay? Okay, let's go down to molality. They're probably not going to ask anything about this, but let's just be sure we know how to do it. So molality, you got to define it. It says, what is the molality? So right away, let's write down what that is. It's moles of solute, which in this case is NaCl, per kilograms of the solvent. And in this case, it's water. And there's a special relationship we talked about in class. And this is only true of water, that 1 kilogram equals 1 liter. So if you go to 7-Eleven, buy a 1 liter bottle of water, it's exactly 1 kilogram. That's only true for water, okay? So I'm going to write water up above this. All right, so that helps us to convert from liters here. We have milliliters into kilograms, which is what we need our answer to be in. Okay, so what do we start with? We start with 45 grams of NaCl. And we need to get to moles of NaCl on the top. That means we need to use a molar mass conversion. And so we figured that out earlier. And that is that 1 mole for every 58.44 grams for NaCl. Okay, so now we got it in moles for NaCl. Now we got to take care of the liters to kilograms. So first thing we're going to do is convert this into 200 milliliters. The other thing I could have said is that 1 gram equals 1 milliliter. That's the same thing. These are 1/1000th of these two units of measure. So I could have said 1 gram. So let's go ahead and do that one. So it's times what I could have put over here, underneath here in the denominator, is the 200 milliliters. So we have 45 grams in 200 milliliters of water. Okay, so over here, I'm going to put that there's 1 milliliter of water for every 1 gram of water. So we'll put H2O. So milliliters of H2O cancels with milliliters of H2O water. And now I got to get grams to kilograms, so that's going to be 1,000 grams. Again, I'm running out of space, so I'm not going to put water. Equals 1 kilogram. It's 1,000 grams of anything equals 1 kilogram. So grams cancels with grams. And you end up with kilograms on the bottom, moles of NaCl on the top, which is what you want. And that's called molality. So now we multiply 45 times 1 times 1 times 1,000 divided by 1 divided by 1 divided by 58.44 divided by 200. And I get 3.9. So I'm going to write the answer down here. It's 3.9. And there's the units of measure. And you express that as small m, molality. Okay, moles of your solute divided by kilograms of the solvent. Okay, so again, practice these. Write them out. Be sure you can do it without looking at this. Don't just watch it. You got to actually do them. Okay, mass percent. Now we're going to move on to mass percent. We'll do one of those. What is the mass percent of 56.7 grams of SO2 dissolved in 845 grams of water? So what it's going to be is the mass of SO2 over the mass of SO2 plus the mass of water times 100%, because it's a percentage. It doesn't matter what units of measure you use. For mass, it could be grams, kilograms, as long as because they're all going to cancel out. You're going to have grams over grams, it's going to cancel out. Okay, so what we're going to simply do is say 56.7 plus 845. And what you get is 0.063. And that's a fraction. That's a decimal now. Now convert it to a percent. Slide the decimal over 2 places. That's basically multiplying it by 100. And you get 6.3%. Don't use the percent sign on your calculator. Forget the percent sign. Just multiply it by 100 and then attach the percent sign to the end of it. Okay, so that's the mass percent. Mole fraction. That should have gone on the next page. So let's go on over there. What is the mole fraction of 1.2 moles of copper oxide and 67 moles of H2O. It's done the same exact way, except it's not expressed as a percentage. So it's simply going to be, I'll do this quickly, 1.2 of that over the entire thing. 1.2 plus 67, and if you add all that up, you get points. You get you get 0.018, and you just leave it like that. Okay, and that's used in areas of chemistry that are not covered on the AP, nor did we cover them in class. They're not hard, but they don't test them. Okay, parts per million is just like a percent composition by mass, except instead of multiplying by 100, you multiply by 1,000. So what is the concentration of parts per million of 4 grams of sodium hydroxide in 895 million, 1,000 rather, grams of solution? So yeah, the solution means the sodium hydroxide plus the water added together, so they've already done the addition for you. So it's simply going to be this, 4 over okay, again, commas are just a way to make the number more readable. It doesn't change the value of the number. And what you get is 4.5 parts per million. So for every million molecules of the solution, you have 4.5, not really molecules, it would be, it's going to be in a compound, but particles of NaOH. Okay? All right. Okay, we're going to do a couple of complex problems, which the word complex in this context just means it ties several concepts together. You might find them to be complex, but it really just means they tie several concepts together. Okay, so styrene, compound substance used to make styrofoam cups, contains 92.3% carbon and 7.7% hydrogen by mass. So one thing you can see by that is those are the only two elements in that, because 92.3 plus 7.7 adds up to 100%. So you don't have anything other than those two. And has a molar mass of 104 grams per mole. So that means 1 mole of styrene equals 104 grams of styrene. That's the way we'd write it in the way we've done it. Okay. This is the same as saying 1 mole. Yeah. Okay, there you go. All right. So, the question is, we want to find out what the empirical formula and the molecular formula is for that. Okay. So let's go ahead, and the first thing you do anytime you're given something in mass percent, what you do, this is the key to doing mass percent, otherwise you won't be able to do them. You take an imaginary sample of 100 grams. So if I have 100 grams of styrene, that means, so let's just assume, you just write the word assume, you get to pick how much you're going to work with. You could work with 100 grams or 1,000 grams or whatever you want. So assume 100 grams of styrene. Okay, so what that means is if you have 100 grams of styrene and 92.3% is carbon, then that means you have carbon is 92.3 grams and hydrogen is 7.7 grams. And now if you're going to work with a chemical formula, you got to get it into moles. Chemical formulas, chemical equations, compounds, they don't understand grams. So let's right away do that. So we know that we have 1 mole of carbon for every 12.01 grams of carbon. And let me just write this one down a little bit lower. For hydrogen, from the periodic table, that we know that we have. Okay, so if we divide for carbon, I'm going to try this again. I made a mistake here. 92.3 divided by 12.01. That gives me 7.7 moles of carbon. And for hydrogen, we have 7.7 grams there. Divided by 1.01 per hydrogen atom is 7. So 1 mole for every 1.01 grams of hydrogen. And you end up with 7.6. Okay, so now what you do is you make a ratio of these two with the smallest number on the bottom. So for hydrogen, it's going to be 7.6 over 7.6, which equals 1. And then for this one, it's 7.7 over 7.6, which equals close to 1. We're going to say close enough. Okay, we didn't get exactly 7.7 here, but that's close enough to 1. How do you judgment? 10%, 5% maybe. If you're off by 5%, this is within 5%. So that's good. So what that means is our empirical formula is this. We have 1 carbon for every hydrogen. So CH is the empirical formula. All right. So how do we do the molar mass? And the formula is you take the actual molar mass, which in this case is 104 grams per mole. And so I'm going to write it over here. So the molar mass of the actual real molecule. CH is not necessarily the real molecule. It's the empirical formula. It's simply a ratio of how many moles of carbon to how many moles of hydrogen. There's a 1-to-1 ratio. But the actual molecule could be C2H2, could be C3H3, could be C4H4. Those are all 1-to-1. So how do we figure out what it actually is? And this is how you do it. It's the molar mass over the empirical molar mass, the molar mass of the empirical formula. And I'll just put MM, molar mass. So I'm going to come back down here and do that. So the molar mass is 104. What's the empirical molar mass? And I'm just going to use round numbers. For carbon, it's 12. For hydrogen, it's 1. So 12 plus 1 is 13. So the empirical molar mass, the molar mass of this empirical formula, 12 plus 1 is 13. So what's 104 divided by 13? And it is 8. So that's what you call the factor. What that means is each of these empirical formula subscripts, there's ones there even though you don't write them, you're going to multiply by 8. So the molecular formula is C8H8. So there's the empirical formula and there's the molecular formula, the actual formula of that actual molecule. Okay, net ionic solution, net ionic equations rather. And net ionic equations are long problems. They won't ask you to do one of these entirely on the AP, but they could ask you to do parts of it. And you should recognize how to do a net ionic equation. So I'm just going to give you a simple statement here. Write a net ionic equation for the reaction of lead 2 nitrate with potassium iodide. That's actually one that we mixed in class. That's what gave us that yellow precipitate that sank to the bottom of the beakers. Okay, so there's a lot of steps involved in this. Again, they won't give you all of them to do on the test, but they could give you some of them. So let's go through what they are. The first thing is write the formula for each reactant compound. So you have to be able to take these names and you have to be able to, these two names, and convert them into a chemical compound formula. So lead 2 is Pb2+. So if you go, what you should have for this, by the way, let me point this out, it's up at the top. You should have a periodic table, and you should have a periodic table of charges. Okay, so here's what you should have. You should have your 60 ion sheet. That's the one I really like because it not only has charges of individual element ions, but it also has these covalently bonded ions like phosphate and nitrate and sulfate. So I would have that one out. You should have, then you can also have your charge numbers of ions. I tend to prefer the 60 ions, but this does have some elements that are not on that sheet, but it's only elements. But have that out too. Next thing is you need to have solubility rules, okay? So you have to have that out. And finally, you should just have a regular periodic table out. Okay, so what a net ionic equation is it is an equation made from ionic compounds. That means you have a cation, a positive charge, connecting to an anion, a negative charge. Okay, so let's go ahead and let's do this step by step, and then I'm going to give you one to do on your own. So you're going to write the formula for each reactant compound. So lead 2. So if lead 2 is just telling you what the charge on it is. So there it is right there, is lead 2. So you're going to write lead 2 and nitrate. So what is nitrate? So come to this sheet again. Remember, you get to use all these sheets on the test. Nitrate is NO3 minus. So you have a 2 plus up here and a 1 minus there. So you're going to need 2 of the minuses, 2 times a minus, to equal 2 plus. You need 2 charges of this, 2 of these, to balance with 1 of those. Okay, so that means the chemical formula for that is going to be Pb, because that's a 2 plus, NO3, but you need 2 of them. So 2 of those negatives is going to balance out with the 2 plus of the lead. Okay, there it says right there. All right, potassium iodide. So come on over, and you ought to be able to do this just from your periodic table. But anyway, let's use this. We've got it. K plus. It's a plus 1. It's a 1 plus, and iodide is a 1 minus. So they're going to match up 1 to 1. So that's going to simply be Ki. The plus 1, the minus 1, they balance already. So there's your reactants right there. Lead nitrate and potassium iodide. So the third thing you do is you write the reactant side of the equation. So it's PbNO3 2 plus Ki. Okay, next thing is, this is a double replacement reaction. So it says write the product side, that's the right side, by switching the cations Pb and K with the anions NO3. So this Pb is going to come over and switch places with this K. So that means Pb is going to be together with I, and K is going to be together with NO3. So you go ahead and you write them PbI and KNO3. All right, so notice one thing here. K is a plus 1 and NO3 is a 1 minus, so those balance. But Pb is a 2 plus and I is a 1 minus, so they're not in balance. That means you're going to need 2 of the iodines to balance with the Pb. So Pb 2 plus and I 1 minus are not charge balanced. So now you have to use that to determine the subscripts. And you can use the 60 ion sheet. So 1 Pb2 plus balances with 2 I minuses to produce PbI2. 2 plus, 2 times 1 minus. So that's how you determine the subscript. And we already said that 1K balances with the NO3. So you have K. K is a plus 1. NO3 altogether is a 1 minus. And so those are your products right there. So you write them right there. So now you have the complete equation for this. Okay. Next step. Again, you get to work on everything with this type of problem. Next step, you got to balance the equation. You can't do anything with a chemical equation that's not balanced. So you see, it's already balanced here, but you had 1 lead and 1 lead. You had 2 iodines here and only 1 there. So you had to put a 2 out in front there. That 2 applies to the iodine. It also applies to the potassium. So 2 potassiums means you have to put a 2 out in front of the K, and that 2 also applies to the NO3, so that puts the NO3 in balance with the 2 NO3 here. So this 2 NO3 balances with this 2 NO3. So everything's in balance, so that's a balanced equation. Alright, now you have to determine which of these are soluble, which ones are going to dissolve in water. So let's look at it. PbNO3, and that should be a small 2. So let's look at it. Come over to your solubility rules, and let's review what these are saying. These compounds or elements or ions are always soluble in water. Remember, these are solubility rules for water, not for anything. For water. Okay, and these are soluble in anything. No matter what these are attached to, they will break off of it and they will dissolve. These are soluble with everything except these 3 cations. So you need to check and see if you have this, is it attached to one of these 3? If it is, it won't dissolve. It will if it's dissolved to anything else but these 3. Same with sulfate. Okay, it's soluble with anything except for these 5 cations here. Okay, when you come over to the other side, these are things that are insoluble. Well, the exceptions for insolubility are these. These are always soluble, in other words. These are always soluble. Okay, these are insoluble except when they're with Ca, Sr, or Ba. So, for example, if you have Bas, that would balance, be charge balance there, Bas, that will dissolve. But if you have any other 2+ with that, it won't dissolve, okay? Except these 2. All right, and finally, carbonates and phosphates are not soluble in water. They just don't dissolve in water, okay? All right, so let's figure it out. So PbNO3. So NO3, it says, is soluble with everything. Everything, no exceptions. So that is soluble. So we're going to say soluble. Ki, potassium is soluble with anything. So Ki is soluble. PbI2, that should be a small 2. Well, let's come over here. I is soluble with anything unless it's attached to Pb. That means if you have a compound of PbI, lead iodide, it will not dissolve. This dissolves with anything except these 3 guys, and it's attached to one of those 3 guys, so it will not dissolve. So PbI2 is insoluble and will form a solid precipitate. Precipitate means it's a solid that, generally speaking, sinks to the bottom. That's what the word precipitate means. Finally, KNO3. Again, K dissolves with anything, doesn't matter what, and then so does NO3, so that's going to dissolve. So all of them are soluble except for PbI2. So now what we do is we write a complete molecular equation. Now, even though these aren't molecules, and we talked about the difference between molecules and formula units and crystal lattice structures, they look like molecules. They look like separate units. They call it a molecular equation, but they're technically not molecules. They're ionic units. Okay, anyway, let's not go there. So what you do is you need to put the states down. So the ones that won't dissolve, or excuse me, the ones that will dissolve, and there's 3 of the 4 up here that will dissolve, pull it down, will be what's called aqueous solution. It means when they hit the water, they break apart. Now, how does this break apart, just as a point? Does it break apart into a Pb and an NO3 molecule? No. It breaks up into a Pb, an NO3, and a second NO3. So there's 3 particles in all. The NO3 doesn't break up, but one NO3 breaks off. There's 2 of them. One of them breaks off, NO3. Another one breaks off, NO3. And then they separate from the lead Pb. So you end up with 3 particles in all. Okay, that's aqueous. It means it dissolves in water. So these really aren't together as a compound. They would be if they're on dry land. They will stick together because they have charges and they'll stick together. But in water, they get pulled apart totally. So they're really not PbNO3 as a compound. They've come apart. 2Ki, potassium iodide, same thing. When this hits the water, potassium iodide, it comes apart. Totally breaks up. The PbI2, though, doesn't. That's the one we said does not dissolve in water, so it actually forms a compound. And it's a solid, and so it's going to sink. It doesn't necessarily have to sink because it's a solid, but it will sink. And then the KNO3, again, these fall apart. They dissolve in water. Both of them do. So that's aqueous. So what that means is you're going to have 2 potassium ions and 2 NO3 ions in the water. Okay? So that's how you write the molecular equation. Now what you can do is write the long one. That's the complete ionic equation. So here's what you do. I said that you had a Pb, so there it is, and you can go ahead and write the charge number up there and write aqueous. It's a 2+. You end up with 2 NO3s. Those break apart. So the way you write that is you write NO3 with a 2 in front. That means 2 separate NO3 ions, and it should have a little minus sign up there. And that's aqueous. And then you have 2 of the potassiums. There's 2 potassium ions. You have 2 of the iodines. There's 2 of the iodines. And then over here, this does stay together, so you don't separate it. That is a solid compound. Then over here again, you have 2 potassiums and 2 nitrates right there. Okay, so the last step in this is to get rid of the things that are the same on both sides. If you have 2 nitrates on the left side and 2 nitrates on the right side, the nitrates didn't do anything. They broke apart here, they stayed broken apart here. The same is true with the potassiums. They broke apart here, they stayed broken apart here. Now for the lead and the iodine, they didn't. They got together and formed a compound. So the ones that broke apart and stay broken apart are called spectator ions because they're just watching the reaction. They're not really being a part of the reaction. So you basically put a line through NO3, NO3. You put a line through K+, K+, 2K+, 2K+, and what you have left is the lead, the iodine, and the PBI. So you just write those down there. And that's the Net Ionic Equation, okay? So a lot of things were covered there. And so we're going to do another one, and the other one I'd like you to practice every day between now and the test, because as I say, they're not going to ask you for one of these entirely, but they could ask you, they will almost definitely ask you for bits and pieces of this, okay? So there you saw that example. So let's go ahead and do this one. So sodium chloride and lead 2 nitrate are combined in a solution. Write the Net Ionic Equation. Okay, so here we go. So write the formula for each reactant in the compound. So lead 2. So again, pause and try to do this on your own as much as you can, and then just watch me do it as you need help. So lead 2 is going to be Pb, just like the last problem, Pb2+. And nitrate is NO3 minus. Again, where do you get that? Right here. Pb2+. It could be 4+, but since it says the Roman numeral 2, it's 2+. And nitrate, again, we used on the last one, and it's right here, and it's NO3, and it's a -1 charge. Okay? So what that means is we do use our crisscrossing arrows method, and we call this Pb with a 1, but you don't have to write the 1. And then you're going to need 2 nitrates, NO3 parentheses 2. So 2 of these -1 charges gives you -2, and 1 of these +2 charges gives you +2, so +2, -2 balances. Okay, what about sodium chloride? That's Na, and that's a 1+, and Cl is a 1-, so those are going to match up 1-to-1 as we know, and that's NaCl. Sodium chloride. Okay, so now we're going to write the reactant side, and we're going to write Pb okay, and there it is. That's the reactant side. Now it's a double replacement reaction, so we're going to swap dance partners here. This cation is going to come over and take the place of this cation, and they're going to swap places. So now what you have is write the product side. So that's going to be Na, NO3 plus Pb Cl. Okay. So now that's the product side. That's what goes over on this side of the arrow. Now we have to be sure it's charge balanced. So the Na is a 1+, and the NO3 is a 1-. Okay, so that's charge balanced. The Pb is a 2+. The Cl is a 1-. So you're going to crisscross the arrows. You're going to need 2 Cl's to balance out with 1 Pb. And so that's going to give you Pb Cl2. 2 times 1- is 2-, and 1 times 2+ is 2+, so 2+, 2- balances out. And these two just go together 1-to-1. Okay, so now we can write the entire equation down here. Actually, I kind of did what I was supposed to do down here. I did it up here. That's okay. So let's go ahead. It says write the entire molecular equation. So there we go. Here's the products. and then here's the reactants over here, that and that. Okay, so there's your complete molecular equation. Now we have to balance the equation. So let's just take a look at it. We have 1 Pb, 1 Pb. Na, we have 1 Na, 1 Na. NO3, we have 2 NO3s there, but only 1 over here. So we're going to need to balance that. So we're going to put a 2 right here. So we have 2 NO3s and 2 NO3s. Now that put our Na out of balance. Our Na is 2 Na there and 1 there, so we're going to need to put a 2 there. So we now have 2 NAs and 2 NAs, but now we have 2 Cls there, but we do have 2 Cls over there. So everything's in balance, okay? So it's 1, 2, 2, 1. So let's go ahead and write that clearly. Okay, and there you go. That's your balanced, complete molecular equation. Next step. Which compounds are soluble? So now we're going to write the state that they are in, which ones are soluble. So let's get our solubility rules. And let's go here. So PbNO3 is the first one. And NO3 dissolves with anything. So that's going to be soluble. So that's aqueous. How about NaCl? Well, that's salt, and I think everybody knows that's soluble. That's aqueous. Let's put it this way: if these reactants were not soluble, this whole reaction would come to an end. It wouldn't be able to work. Now, how about NaNO3? Well, both Na and NO3 are soluble, so that's aqueous. It means they're not really going to form a compound in water. They'll form a compound on dry land when they don't have water molecules around. They'll stick together, cation, anion. But underwater, they won't. They'll fall apart. And then PbCl2. Okay, so we see that Cl is soluble with everything except 3 cations, three elements here, and one of those is Pb. So that means this is insoluble. So that's going to be the solid. That's going to be the precipitate. Okay, so there we go. So I actually answered that question up there. All right. So write the complete molecular equation with states. Well, I did that already. I'm not going to do it again. So it's right there. Okay, you got the complete molecular equation with states. Now write the complete ionic equation. This is the long one. So here we go. Okay, so we've got Pb. It's a 2+, and it's aqueous. Okay, I'm just going straight down the line here. Now we've got an NO3, but remember, those aren't going to stick together like an NO3-2 molecule. They're going to come apart too. So you have 2 NO3, and they each have a minus charge, and they are also aqueous. Now you're going to have 2 NAs, and they're cations, they're positive, 2 Na plus 2 Cl minuses there. And I should be writing aqueous and aqueous there. Everything's aqueous on the left. Okay, now we get 2 NAs and 2 NO3s. So again, 2 Na plus 2 NO3s minuses. And those are aqueous. And finally, you've got your precipitate, which you don't write separately because it does actually stay together. That's PbCl2, solid. Okay? So now the last thing you do is you go through and you look for, here's your arrow right here. So you look for things that are the same on both sides of the arrow. So 2 NO3 cancels with 2 NO3. 2 Na cancels with 2 Na. You don't have 2 Cl on this side, so it's by itself. Pb2+ you only have on this side, and this precipitate you only have on that side. So your net ionic equation is going to be the things you didn't cross out. Pb2+, aqueous. Okay, and that's your final answer, your net ionic equation. But again, they could ask you to do bits and pieces of this on the test. So if you can do this every day or until you feel like you really know how to do it, and you may see this good, decent chance you'll see this on the test. Okay, let's keep rolling. We're looking at 1 hour and 18, and we're going to finish this up right here. Okay, it's a limiting reactant problem. Remember, if it takes 2 eggs and 1 cup of sugar to make 1 cake, and you want to make 10 cakes, then you're going to need 20 eggs and 10 cups of sugar. You'd have to multiply everything by 10. But what if you had 20 eggs and only 1 cup of sugar? Well, then you have only enough to make 1 cake. You have plenty of eggs, but you only have enough sugar to make 1 cake. So the sugar is a limiting reactant. It's keeping you from making more than that 1 cake. You'll have a lot of eggs left over. Those are called the excess reactants in chemistry. And the limiting reactant is the sugar, because that's what kept you from making more cakes. All right, so that's what this is. Generally, you're not given exactly the right proportions of chemical reactants in order to make them all react equally at the same time and end up with have used them all up at the same time. So, first thing we need to do is balance this equation. Okay, and let's see, I think I may have changed the question a little, but let me do this. Okay, so I have 2 carbons here, I need 2 carbons here. I have 4 hydrogens here and 2 here, so I need 2 there. So now hydrogens are in balance, carbons are in balance, and the O2, I have 2 times 2 is 4, and 2 times 1 is 2, so 4 plus 2 is 6, so that means I need to have 3 there. So I have 6 oxygens, and then 4 plus 2 is 6 oxygens, 4 hydrogen, 2 carbon, 2 carbon. So there's a balanced chemical reaction. Okay, so what's the question asking? It said, how many moles of CO2 can be produced from 10 moles of C2H4 and 8.7 moles of O2. Now, I could have made this a little more complicated by giving you grams, then you would have to convert to moles. Remember, you can only use moles in a chemical equation. Okay, can't use grams. Okay, so what you're going to do is this. Draw 4 boxes. You're going to draw 2 boxes underneath C2H4. Again, you'll see online, if you go to YouTube, you'll see different ways people solve these. Some people use ice tables. I just like this. It's kind of a graphic organizer. It's kind of visual. Okay, now we're going to have, all the methods have in common, though, is they run the reaction twice. You have to run the reaction twice. The first time, you use all of the first reactant, C2H4. The second time, you use all of the second reactant, O2. Okay? Now, since we're already given moles, we don't need to do any conversion. So what it's telling us is this. It's telling us we have 10 moles of C2H4. We know we have that many moles of C2H4. So under C2H4, in the all C2H4 row, I'm going to put 10 moles. These numbers represent moles. Because I'm assuming this is the reaction where I'm going to use all of the C2H4, and that's 10 moles. So that's how much I'm going to use. I am also given 8.7 moles of O2. So I'm going to run the reaction a second time where I use all of the O2. So you go to the O2 column, and in this row right here, you put the 8.7. So this reaction assumes that I use all the O2 I was given. This reaction assumes I use all of the C2H4 I was given. Now what you have to do is just fill in these boxes right here. Okay, so what is this telling you? Remember, you don't just look at this as, and I like to put a 1 there to indicate that that is a number of moles, 1 for 3. It doesn't mean you have to have exactly 1 mole of C2H4 for every 3 moles of oxygen. It just means you have to have 3 times as much oxygen as you have moles of C2H4. So if I want to use up all of the C2H4, how many moles of oxygen am I going to need? I'm going to need 3 times this much. I'm going to need 30 moles. In order to use up all of the C2H4, that's how many moles of oxygen I'm going to need. Now, in this one, you go in the other direction. You need 3 moles of O2 for every 1 mole of C2H4. So if this represents the 3 times, so this number is 3 times this number, just like this is 3 times this number. So if I take a third of that, that'll tell me if I'm going to use up all the oxygen. That means I would need to have 2.9 moles of C2H4. Okay? So the next step is you go around and you just give yourself a yes or no. Do I have that many moles or more, at least that many moles of each of these? So first, do I have at least this many moles of C2H4? Yes, I have exactly that many moles. That's how many we were given. So you can put a little yes there. How about this? Do I have at least 30 moles of O2? Well, the answer is no. I only have 8.7 moles of O2. I don't have enough O2 to burn all of this, so I'm going to put a no there. Now I'm going to keep going. Do I have at least 8.7 moles of O2? Yes, we just said that's how many you were given, so yes, you have that much. And finally, do I have at least 2.9 moles of C2H4? Yes, you were given 10 moles of C2H4, so yes, you have way more than 2.9. So yes, you have at least 2.9 moles. So the reaction that could actually run is the one where you have enough of each of the reactants to make it happen. And that's the one on the bottom. You can't run this reaction because you don't have enough oxygen to burn all of that. So that you're going to run out of oxygen because you were only given 8.7 moles. So that means you're going to have C2H4 left over here. Okay? So to make this one, so this is the reaction that can actually run. So the row that has the 2 yeses in it is the reaction that will actually work. And the column that has the no in it, that's the limiting reactant. That's the one that's running out first. It's the oxygen that's going to run out first before the C2H4. So what is the limiting reactant? It's O2, because that's the column where the no is. It's that. You're going to run out of that first. How much of the non-limiting reactant is in excess? How much do you have left over? Well, this is the reaction that'll work. And if this reaction works, we're going to use all of our O2. That's how much we were given. And we're going to use only 2.9 moles of our C2H4. But we were given 10 moles. So if you take 10 minus 2.9 equals 7.1 moles of C2H4. That's your excess reactant. And that's how much is left over. You were left over with 7.1. Now, how many grams of H2O can be produced from these reactants? Well, you ignore this reaction. It can't be run, so skip that one. You come down to the bottom one, and now you first of all just find relations between moles. So you could pick either one of these. You have 1 mole of this, 3 moles of this, 2 moles of this, 2 moles of this. So what you simply do is this. I want to know H2O. So I have 2 moles of H2O. I get 2 moles of H2O for every 1 mole of C2H4. I'm going to end up with twice as many moles of H2O as I have moles of C2H4. So how many moles of C2H4 did we burn, or did we react? We reacted 2.9. So that means I'm going to be able to get twice that many moles of H2O, so that would be 5.8 moles of H2O. Okay? So you end up with twice as much of this as this, so twice as much of this as that. So now, but it's asking for grams. I made it more difficult, so you'd say 5.8 moles of H2O times 18.02 grams. Okay, again, you know how to calculate molar mass. H2O for every 1 mole of H2O. Okay, and that's going to be moles of H2O. Now it's 5.8 times 18.2. And that gives you 104.5 grams of H2O. Get that on screen there, okay? All right, one last problem and we're done with this set for today. Okay, how many grams of CO2 will be produced from this reaction? So, it's the same thing, okay? except you have a different molar mass for CO2. You get twice as much CO2, 2 moles for every 1 mole of this. So this number is also going to be 5.8 because these two happen to be the same, so 5.8. So it's 5.8 times 44.01, and if you do that, you'll get, just give you a check figure if you want to do it, and that's going to give you 255.3. Okay, so this is my assignment. I'm going to give you some problems from the AP classroom, maybe later today, maybe tonight, maybe just later in the week. I mean, this is long. We're at an hour and a half right now. So I want to get this up. I want you to practice these. I think we covered just about every type of reaction except redox reactions, which we did not get to in class. Some of you came for some of the after sessions. We did a little bit, but not enough, so I'm not going to cover those. And acid-base, I'll do it another day. We did cover those, and I'll do those on another day. Okay, so practice these, get really good, and I'll see you on Sunday.